Professional Chapter Pune to felicitate our distinguished keynote speaker, Mr. Umakant Kapoor, as student chapter has won Outstanding Chapter Community Service Award, and it is the first national accolade. To give us a glimpse into the vision and impact of ACM, we'll now have the ACM video presentation. May I request the technical team to please play the video. Thank you so much. That was truly inspiring. We will now felicitate the office bearers of ACM Professional Chapter Pune in recognition of their invaluable contributions. I now request Dr. Sonali Patil to felicitate Mr. Nitin Patil, Chair at Pune Professional ACM Chapter. Thank you so much, everyone. I now request Mr. Nitin Patil, Chairperson at Pune Professional ACM Chapter, to address the gathering. Please welcome him with a huge round of applause.
We started this professional chapter newly formed body, looking from October. I am happy that PCCOE granted us to conduct this first event along with student chapter. So I am thankful to Surya Madam and I am also thankful to both the speakers who generously accepted invitation and thought of giving some lights, open lights overall to both the topics of Agentic AI and quantum computing. So as most of you are student fraternity, so it would be great to work with both these domains, and you definitely will be seeing so many kind of such events definitely in further months. Thank you.
Thank you so much, sir, for those valuable words and continuously supporting and guiding the student community. Moving ahead, it is is now my privilege to introduce our first keynote speaker, Mr. Ambarish Deshpande. He is an M.Tech in software engineering from BITS Pilani and currently serves as Senior Practice Lead AI for the Sirius Tech Healthcare Technologies. With over 20 years of experience in enterprise architecture, including 18 years at TCS, he has applied machine learning and generative AI to complex challenges in healthcare, insurance, and retail industries. He has also published multiple white papers on AI, bridging academic research with real-world enterprise adoption. We are honored to have you, sir. Sir, may I now let us welcome him with a huge round of applause.
Hello.
Okay, as soon as the PPT is up, I will show that video and then talk. Is it okay?
Yeah, go ahead. Okay, so I am not a professional speaker or a teacher, so you have to be interactive with me. I am very unhabitual of not having unhabitual of these things. So please be talking, okay? Comfortable? All of you good with me? Yes. Okay, so if I'm asking a question, you will that. Okay. So what is agentic AI and why you want to learn it? This is an important question you have to ask at least in your day now. Because what? You would want to know. Alright, all good? No. Please be on just 1 minute. I'll just start with the laptop. Okay, I think we should start. Meanwhile, laptop will start. Okay, so let's take a topic of agentic. All of you with me? Yeah. Okay, let's start. So, how many of you are really aware about generative AI? Can you raise the hand? What is Gen AI? All of you are aware? Not. I think ChatGPT has more users than Facebook for God's sake. Come on. All of you, right?
Yes.
Good. Okay. So, what is agentic AI? What is generative AI? These are the core things which we have to observe today. But this is not new thing in the industry, okay? So I will not be able to tell you how that model is being trained and all. I will be giving you very practical things which is happening in the industry right now. Okay? Very, very practical things. And the reason of that is, okay, anybody know why somebody should know agentic AI? Anyone? Or students? Lecturers know. Yes?
Because this platform assists the person to conduct his task in more efficient way, because they are designed to work autonomously on a particular task.
That's an excellent word that he used for us, autonomous. Autonomicity is extremely important. But automation was always part of computing systems, isn't it? How does that make agentic AI different than what we were doing earlier? We were automating stuff, isn't it? We were doing Excel sheets to databases, we were creating microservices, we were creating machine learning models to do what? Automation. Then where exactly agentic AI fits in? That's very important. And autonomicity in which angle, in which prospect? That is also very important, isn't it? So when we are migrating from this normal automation to an agentic AI based automation, that is important to understand, isn't it? So we need to learn agentic AI not because it's great salaries. Of course, you're gonna get that. There is no worries on that. But we need to learn it. It's gonna be a transformation technology like internet. You missed .com race because you were not born at that time. I was. So .com was like 2000. In 2000, everybody wanted to create a website and be online. At that time, creating website was a big thing. Creating e-commerce was a big thing. Amazon came with a great idea that book can be sold online. And Jeff Bezos actually created a website. You know how much time it took for him to create a scalable website? 6 months. You can create that kind of website today in 6 minutes. Right? Just few prompts away. Why? Because of agentic AI, not generative AI, agentic AI. There is a huge difference between agentic AI and generative AI. We need to understand that. But let's take step by step. Smart point.
That's it.
Okay, so these different things which we were talking about is okay. Somehow it's not associated with me properly. So earlier we used to have process automation. You were not born at that time. Automation was a thing. Okay, so we also have some softwares for creating an automation processing like navigating Excel, navigating documents, or creating normal processes in an automated way. So this is process automation. We are doing Python scripting for that, or R scripting for C++, C. All those languages were used. There was languages before you is Fortran, Pascal, Basic, and COBOL, and if this is French, it's okay. Now we actually shifted this particular process automation to supervised AI ML. What is supervised? What is supervised? We guide them. Okay? You have a supervisor. Why supervisor? Supervisor is guiding you to go something, to do something. What is correct, what is incorrect? We guide it. So that was a second era when we used to have a training data set. Okay? A training data set, we are creating a model. That model is getting translated to automation processes, and that is getting converted to machine learning model. We know this. Why I am telling you? So I am telling you because this makes a new of software computing where algorithms were not written, algorithms were understood by a machine. Yes? Then came generative AI. Generative AI is a combination of machine learning, combination of deep learning, combination of NLP. Right? And together we created something which actually talked to us. come back, create next token, create new image, create new video, create something new. Up to this point, the power with humans, that everything is created by us and machine was just repeating what we are saying. But now we have power to create something completely new, right? That was the power of GenAI, but GenAI was not useful for industry. Why? Because industry do not need creation. Industry 80% of time depends on repetition. Correct? Let's say manufacturing industry, you are creating a car once. You are producing that car for 10 years. Industry, the 80% revenue comes from repetition, but the repetitive task was not able to handle. Your generative AI was not doing that. Who was doing that? AI ML was doing that, automation was doing that. So there was a missing link between creative processes and automation processes, and that mixed up. Understood? That mixed up in the last layer, which is called as agentic AI. Correct? And have you heard a sentence from, I think it's from Forbes magazine, that 98% of AI projects actually failed. Read that? 98% of AI POCs failed. When I went back to my leads, my CEO, Mr. Rajan, I told him that this is something a magazine is telling, then he told me one more sentence. You know, there is a story of Thomas Alva Edison that he tried a bulb 10,000 times. And then one time he got successful. That's what is industry doing right now. 98% failure is actually giving 2% of success stories, which will get a transformed industry in the future. Yes or no? With me? So look at that perspective. Don't look at like 90% fail. Those failure use cases like industry is trying something new, and this trial is extremely important, and that is what agentic AI. So what is different? What is different in agentic AI is literally recruiting an AI employee. Literally recruiting an AI employee. And look at it this way, that you are actually hiring a person to do a task for you. So if you are hiring a person to do a task for you, what are the things that person should know? Correct? That person should know your task details. Correct? So the task detail, if you give it to that employee, then he will try and execute it once. He will fail. You will tell him that this is not right. Yes? And then he will correct it. And again do that. And again we will try it. And that go on for a while. Correct? That is an agent for you. Agent has a self-reflection mechanism. Agent can detect what output he is generating against the goal he is supposed to deliver. And using he is my bias. Please do not do that with me. Okay? Just like agent is he for me. Okay? And LLM is she for me. Because LLM speaks. Okay? Okay. So goal, a plan, action and reflection. If you follow these 4 steps, you will get what? An appropriate agent. The plan is ingested with what? Data. If I give a plan to you, if you are doing an engineering, if you have a course in front of you, can you do anything with that course? Nothing, unless you have what? Books, reading materials. That is the data. Yes, sir.
I'm not an expert, but how is that different from a small language model, which is a native, which is sitting on your chip, you don't need any external science, and then you keep updating the database of that model with your own inputs, like.
Great question. Very good question. Thank you, sir. So any SLM, which is small learning model or small language model, any large language model or AI model is a combination of probability. You teach new vocabulary to it, the tokens are ingested into it, it's going to give you. So when you create a new model, it will give you new vocabulary, not new knowledge. Getting the point? So if I am training a model with insurance domain, it will understand what is limits. Okay, so limits for mathematician, limits for physician, and limits for insurance guy is completely different. So my model will start understanding limits. what is the limit of your policy and my policy, that is understood by agent.
So is it a combination of the supervised AI and the
It's a combination of supervised AI, generative AI, and a model which can understand all tools. You will take to the next slide. Okay. So yes, SLM, LLMs will improve their vocabulary in future, but the niche data which your industry works on cannot be actually ingested into the model. Context awareness. So context is always niche, and you cannot rely on any model for facts. Model is just a combination of probabilities. Okay? So this is what is happening at the agent. So this is how agent, I love to have a simple slide for you. This is extremely important. You have an agent. Agent is nothing but agent have all this periphery. Agent have tools, agent have goals, memory, actions, observations, and environment. If I say all these things, these are junk for you. Let's understand this. On the employee perspective, I have an employee, okay, and that is called as agent. If I am not giving him any tool to work on, then how can he work? He can't. Tool can be anything. It can be knowledge, it can be processes, SOP documents, it can be literally hand-woven tools, right? Without that, he cannot work. The goal, what the employee should do, ultimate goal. Memory, if I am teaching him something or her something, he should remember it next time, not like tomorrow again asking the same details. I will fire him immediately, isn't it? Okay, so you should remember that. Then observation. Observation is if I am performing some task, whether I am doing it accurately or not. If I am not, then I have to go back and again recreate a response and come back. But all these things are basically coming through what? Actions. Action is actual doing thing. So all these things are peripherals. The goals, which is then what I am supposed to do, how I am supposed to do, I should memorize what to do, and then I will also see whether whatever I did is correct or not, but I should do something. That is action. Okay? With me up to this point? What is the brain behind this? Anybody? What is the brain behind agent? LLM. GenAI. Isn't it? LLM is the brain. So ultimately, you have to make your LLM mature. Immature LLM will create immature agents, will create immature output. Yes or no? With me up to this point? Am I boring you? Yes. Okay. So generative AI was what? You log into ChatGPT, you ask write a blog for me, it creates a blog for you, give the result. Did it refine it? No, it's not refining for you. What is AI agent? AI agent have a goal. Goal meaning I have to create a 1500 words of essay for XYZ college. Do that for me, and then you will give tools to him. These are the tools. Like these are the different websites you should browse, and it will actually browse, come back. The context will be added. Okay. You know what is that context addition and fetching the data called in industry? Called as context engineering. You heard about prompt engineering, right? After that, there is a context engineering. So it's a combination of prompt engineering and context engineering creates a better response. With me? Okay. And then you get a final output. It will have a reflection whether final output is correct or not. Agent thinks. Okay? It breaks the task in step by step. You know what is that called? Breaking the task in step by step? Chain of thoughts. Heard of this? COT? COT? Tree of thought, chain of thought? Okay. So that is happening within the agent, and then it will have a self-reflection mechanism to actually create a final output. My audio is enough itself, like I can talk without mine. Is it okay? Like it's unnecessary creating a different output for me. Okay, so if I can speak up to that point, are you able to hear me? Okay, I will shout a little. Fine. So agentic AI is basically the combination of agents working together for the same goal. A college is agentic AI. The combination is actually on the goal of you making a better person and engineer. Yes or no? Say yes. Come on, your lecturers are here. So now this is actually an institution with always an agentic AI combination. So agentic AI works towards a single goal. Why I cannot create a strategic one single agent for all the tasks? It's not possible. It's overwhelming. Can one teacher tell you all the subjects? It's impossible. It's Herculean task, right? So let's divide it. The combination of division is also very important, and that is called a agentic AI. Like how do you combine different agents together to create an organization of agents and work them together? Yes or no? This is an image from internet I grab. I don't know why I did that, but agentic AI basically I want to put it. It will do what? It will identify its what. So that is AI agent. AI agent is a single entity which will perform one task. Okay, it might be an intelligent task for sure, but it will do what? One task. So one task is, okay, I want to give it, it will go, okay, go ahead, find the flight for you and give, or combination of different itineraries and give it to you. Is it booking a trip for you? No. Is it surfing the best price on the internet? No. Nothing is happening like that. But if you convert to agentic AI, I can have a different agent. One is surfing, one is browsing, one is getting the data from different sources, one is comparing. All those things together giving me a combined efficient output. Yes, that is an agentic AI. So that's what I want to see. Otherwise, this is just an internet image. Okay. So that being said, what are the different components? Because all the theory is fine. I also have a practical example for you, like how the actual industry works. But that being said, the 5 core components of agents are these ones. Okay, and let's divide it properly and understand. Okay, this is really important. If you say this in an interview, I will hire you. Okay, so perception model. Perception model use what? So basically, these words are impossible to read. Perception model is how the knowledge is perceived by the agent. The data module. Working it. Then you have learning module. Learning module is the memories component of agent. Getting my point? We will see that in detail. But the memory portion of the agent. Then you have reasoning model where LLM sits. And your most advanced LLM model should be here. By the way, one agent can have utilization of multiple LLMs. If you think that a single LLM is actually forcing agent to do all these tasks, no. It's like you are doing a one combinational project which is have mechanical and electronic and AI and all those things. You're going to have different teachers for that. Yes? And then you're going to get guidance from different teachers. That's how LLM also can be different, because you can actually have a niche LLM for niche tasks. With me up to this point? All of you? You getting bored? No, right? All good? Yes. Yes.
Recently, I was using this agent line. So it has the option of switching between LLMs.
Yes.
So my thought was, how does it switch between context? I mean, we have worked with, let's say, Agentic. It knows my context or what I want to do in the environment, and I am switching to cloud. So how does it move the context from Agentic to cloud?
LLM never understands context. LLM never remembers context. Agent always has the context. Okay? So agent actually have 6 different types of memories. The one is called as, one which is described is called as working memory of an agent. You will see that. Okay? I will answer you at that point. Is it okay? It's a little too with the flow. Okay? But yes, that is an excellent point, that you can actually switch different LLMs to get what? The better accuracy of the response. If the response is getting generated with Claude 3.5 or Sonnet or something else, or Gemini or ChatGPT or whichever model you want to train. Yes? So it is completely possible. If your use case is very niche, then you can have a niche model for doing that. Yep? Okay? So I will answer that question. The reasoning model is basically that. Then finally you have action model. Action model is where agent can perform something. These are the tools, these are the API, the browsing engine, the connecting engine, Alexa. Previously Alexa was only playing songs. Now Alexa can book something for you on Amazon and give you the delivery. Yes, why? Agentic AI. Remember that. And finally communication model. This is the dumbest model. Dumbest. You just put a mini model, GPT mini model there or something else, summarization model, because you know 2000 words of English at max if you have better vocabulary. 200 is enough for communication. And LLM model knows billions of it. So what's the point of having all of ChatGPT 5 and all? Not required. Have a small model there to communicate with you, and you are good with that. Or if you are communicating with a niche person, like an underwriter in an insurance. So underwriter actually understands a completely different vocabulary. Yes? If you are communicating with an Amazon.com employee, then he knows the completely different vocabulary. So if you have a vocabulary specific model, then you can have that in a communication model, right? So if you combine all of them together, you're going to get what? A better agent. Is this the only component cycle? No. There are any number of other things in the periphery. But these are the core components. Okay? Good. Fine. So let's go ahead. Core characteristics of autonomous agent. I got this because you love this kind of questions in the exam. So one thing is independence. The one word you just said, sir, autonomous. Okay. So amount of autonomicity is also important. Like how autonomous it is. Is it independent to actually do everything by itself, or are you adding something called as HIL, human in? Correct. So human in loop. So human in loop is also important. That is actually due to intervention of human. It's important sometimes. Okay. A software fix, software bug, restart of a computer, restart of a server. Do not need human intervention. Why somebody will ask that if I have 8 servers running? You are a computer background, you know cloud. Okay. There are VMs. Let's say we have deployed a software on 8 VMs and I have to restart them one by one. Do you need a human intervention for that? No, it's automatic process. Like unless it is happening, all of a sudden all of them getting switched off, human in loop, and that will be CEO. Okay, don't do that. But one by one, yes, why not? So human in loop is not it, but 100% autonomous. But if I am actually providing a retailer a cashback, $25 cashback, $50 cashback, or refund, or insurance claim, and if I automate that and somebody find a hack, then what will happen? I will be bankrupt on few hours. Yes or no? So we have to decide who designers, architects has to decide how much autonomicity has to be given to an agent. Okay? And you know what? Nowadays we call it as human as a tool, not a human as a loop. Human as a tool. So the perception model, the action model, we can say that human is there to just approve or reject. Even that is an action, and that is the binary input. And we found that 98% of time we are going to do only one thing, either approve or reject. There are very few activities human actually do with that kind of data. Yes, with me? Okay, some more thin slides. So types of autonomous agents. So we have software agent we just discussed, right? Restarting of server, checking logs, monitoring logs, all those things are software agents. Remember this. This is very important. These terms are not gen terms. If you remember this, you're going to crack great interviews. And not only that, you're going to be a great at your projects. And not only that, you will be better understanding of technology. Isn't that important? Yeah, of course. Then next one, robotic agent. What does robotic agent do? Robotic arms, robotic stuff. Nowadays robots are everywhere. Correct? Please. So robots are everywhere. Even our mobile is a very efficient robot. It can record my voice, record my audio, record my video, all those things. Like even noise cancellation, and number of things are happening. That is robotic and a hybrid agent, combination of both. All those warehouses in retail stores are actually getting operated by robotic with AI. They are getting replaced. Okay, a lot of things are happening with robotics. They can move the things easily. Then you have reactive agents. Reactive agents are basically reason and act. So react is a short form of reason and act. It can actually have a logic and action plan attached to it. So these are reactive agents. You have deliberative agent, learning agent, social agent, all those different agents for different activities. Learning agent is basically for memory utilization and consuming the memory efficiently and then attaching to a better agent. There are a number of combinations of doing that, but all these things are very important in understanding the autonomicity of an agent. With me? Okay. But it's okay, whenever you see an agent, you always think like, okay, this is a software where I can give a task, I can give a goal, okay, like line flow, line chain, line graph, crew AI. Anybody know these words or French?
Yes.
French, yeah? No? Who knows? Who knows? Knows. Somebody knows. Okay, fine. So basically these are different frameworks where agents can be written. Okay? Nowadays Google ADK is very popular, Agent Development Kit. Got that? So if you are writing an agent, is it only like an LLM and different things like, okay, this is the task, this is the goal, this is the action, this is the tool and you are done? No, there are n number of layers. So when you do an industrial level project, this is how the agent will look like. This is an intentionally acted the source here. This is coming from Infosys. I don't work for them, but this is a good slide. Okay? So first thing is infrastructure layer. You need to have GPUs. What is GPU? Who do that? Who created? NVIDIA. Good. Nice. So GPUs, the vectors and agent memory databases, API gateways, data engineering pipelines. What is data engineering pipeline? See, 98% project which got failed, right? Which I told you earlier. I will tell you From that, 98% are failed because of the bad data. Yes? The data itself is bad because data was collected in the intention of AI. Data was collected in the intention of collecting it. Because somebody gonna audit that and ask me, like for after 5 years. About after that, there was no use actually. So data is not proper. So data pipeline, data clean, the data pipeline itself is a big box. Our data layer, like data ingestion layer, transformation layer, adjusting layer, clearance layer, cleaning layer, and number of layers to it. And after that, data is consumable by what? AI. What I can offer external services are like different APIs which I can call. After that, there is an operation which is performance evaluation, there is agent traces, tracing, guardrails. Why guardrails are important in AI? Any reason that simple question? Huh?
For the restriction of AI or people in a specific policy or security.
Very nice, very nice. Very simple example of that is, see, if I tell an AI that a doctor is leaving and nurse is holding a doctor for a while, it assumes that doctor is male and nurse is female. Did I mention that? It assumes, and you also assume just now. Yes? Why? Because 98% of internet data is biased. And that's why AI data is biased. Doctor could have been female, nurse could have been male, but we assumed in certain way, that's why AI, that's called as bias. So there is a lot of bias. I'll just give you one example. Not only gender bias, there are other bias also. So AI by default is biased. So there are guardrails. So restrict that. Yes? With me? Okay. Now there is an integration layer. Integration layer is like when, and again here I mentioned you want to do interfaces. Now that name is changed by human as a tool. Okay? So this different integration layer is actually allow AI to do what? To interact with the external systems. After that, there will be a layer of action, which is two-step, RAG empty. What is RAG? RAG.
Retrieval augmented generator.
Retrieval augmented. किसको नहीं पता है? मला राग ही लगा चलो. Retrieval augmented generation is extremely important. RAG. Okay, because this is how the normal context engineering and prompt engineering get married and get a better response out. Okay, then you have prompt library where you will set lot of templates of different prompts, chain of thought, tree of thought, all those prompts going to be there for your system to get designed properly. You have controllers, coordinators, multimodality. Multimodal. Modal is what? Different LLM models, different responses. You need to combine images and text and voice and video. Okay? So nowadays if you Google search, like I need this thing, you know what? It will actually give you a YouTube video and also give you where exactly is being spoken. Right? So video to text conversion, and that text also getting searched with the help of what? It's ultimately RAG. Got it? So that is the RAG. And then after that you have cognitive. Here agent comes. So from this layer to this layer, if enterprise do not have that, all of a sudden will start from here. And they bound to fail. There is no. So you are actually starting a 4th floor without having even the first one, second one, third one, fifth. Nothing gonna happen, right? It's not fair. So this is where the problem lies. So this is where the agent is. Your planning, your agent orchestration, your state, your memories, all of things are there. Okay? So when you are answering those questions, when you are getting knowledge of these things, make sure that you understand the basic things behind the scene, what's happening. If you miss that, you're gonna miss the bus. Because agent is the few lines of code. And that is Copilot generated anyway. Right? I mean, what is the effort in that? Nothing. With me? Yes. Not boring, right? Okay, so agentic memory. So after this point, we just saw that okay, agent have a lot of things, but if agent doesn't have a memory, then it will not remember what you talked about. Why it is important? I'll tell you one important simple thing. Simple thing is, if you are talking to a customer care agent and you spoke very rudely, okay, like with a capital, with a red, I don't know how to speak rudely with the agent, but if you still do that, manage to do that, I want that agent to remember that next time I log in, it will talk polite to me. Yes? It's simple, right? How does that happen? If a physical person do that, it's okay because physical person can understand that okay, this person is always rude, I have to be very polite, extremely polite that way. But an agent remembering that is a big task. And that too, that person can come back after 6 months. And that person can come back tomorrow. Getting my point? So if I have to remember, that is not the only use case, there are many, I just gave you a simple example of that, is with the help of agentic memory. Okay? So there are 6 types of agentic memories here. The procedural memory is a combination of LLM and SOPs, standard operating procedures. Agent should know what she should perform and exact steps. Yes, that is very similar to how your code is written. Step by step. This is what happening. If this happens, then that happens, then that happens. All that if then else conditions and everything will be here. Then you have semantic memory. Semantic memory is for retrieval. It's RAG. Correct? Semantic matching. Then you have episodic memory. What happened to last discussion? This guy talked rude to me. I have to be polite. That is episodic memory. That is episode. Then you have decision procedure. If something happens, this happens. If that rude person asks me refund, I am going to use human in loop. If a polite person asks me a refund, I am going to give the refund. If girl asks me a refund, I am going to get a girl refund. So that's what happens. And then you have working memory. Working memory is basically the memory which this guy talked about. He can change the model dynamically. That is working memory, because agent has to do what? Agent has to cognitively decide what kind of LLM I have to use. Okay, the person is asking about insurance specific detail. Let me change my brain to, and we don't have that choice. Otherwise, we would have used somebody else's brain. Like I would have used Einstein's brain, but that's not happening. But he can do that. So you can actually use anybody's brain. That is working memory. So you can reason with any LLM and work with it. Isn't it awesome? And that makes agent more powerful than me. That will eat up my job, isn't it? But agent cannot do presentation like this. Okay, so yes, these are the different hierarchies, 6 types of memories you can see there, conversion history, working memory, and all those things are there. Okay? Bored enough? Okay, so let's take 2 more slides and I'll give you a practical example. I have 6 design patterns basically. So what is the design pattern? Design pattern is how different types of agents should be created. If I am creating a combination of agents, how that combination should be. Yes, that's an organizational body, like an institution, like this college. So you have a principal, you have a dean, after that you have head of the departments, after that you have lecturers, after that you have presidents of these kind of communities, and then college, like I don't know, classroom monitors, etc. So this is a hierarchy. So how different kind of hierarchies can be made to get an efficient work out of what? Process, agent, agentic AI. Okay, one task, AI agent, multiple task in organization, agentic AI. Remember this? Say this in interview. Okay. Multi-agent workflow, self-reflection, agentic RAG, all those things are different design patterns. Okay? Am I consuming a lot of time, ma'am? Time much, please. Okay, I have time, right? 5 minutes? Okay. So let's take a real problem. Actual comparison of agentic AI framework. This is where you stand out. Okay? If you have to be out of the box, if you have to do something great, this is what you should do. Pick up 2 names, Langra Autogen. Okay, now Autogen is renamed as semantic kernel. Know that? No? Okay, so Autogen is now renamed as semantic kernel. So Langgraph, LangChain, CruAI, Haystack, Google ADK, all those things are different frameworks. You are expected to know at least 2. Because otherwise, how do you actually create an agent? You will not have N8N and all. I don't call that weird thing as agent. Okay, so don't try line flow and N8N. This is bachcha ka game hai sir. Okay, my kid can do that. 8-year-old, he can create an agent for him. Okay, so no N8N please. Okay, and no line flow also. Line flow and N8N, I don't call them agentic frameworks. These are so because you can tune your input and output. You can tune everything. You can tune action framework, LLM choices. All those things can be easily tuned there. Yes? Okay, cool. So let's take a practical problem, very practical, that real that I don't want you to actually take a snap of it. Okay. So last point is A2A. What is A2A? A2A is agentic protocol. So if these agents are working together, they have to talk to each other, yes? And it's good possibility that my entire agentic system, one might be deployed in Google, one might be deployed in my laptop, one in AWS. How they communicate? Getting my point, right? So they have to communicate in a single language. One speaking French, one speaking English doesn't actually work good. So A2A protocol created by Google so that agent can communicate in a single protocol. We generally call this as protocol. It is a protocol. Protocol is the way how agent should communicate to another agent. Okay, the format is actually clear that okay, this is how the different sections should be. We're populating that and it's going to communicate that way, and automatically the next agent will understand and again respond to it. So this is how the protocol is created. That is extremely important. One more word here, but MCP, what is that?
Model context protocol.
Correct. Model context protocols. It's a part of context engineering. Context engineering is how do I call context? Model context protocol is again a protocol, a standardization of calling tools. Okay, so all these tools I don't have to reword and recreate it for every single agent. I can create it once and every agent can call those tools. That is the intention of having MCP. We don't go there, that's not the topic today, but we can actually discuss that. Okay, so last portion of our thing is actually having a practical problem. So do not take snaps now, this is actually industry problem and this is from my last company. So this is a conversational AI assistant required by the user to search and interact with 20,000 articles and documents, and the documents direct from data sources, SQL, PDF documents, all those things are in Google. Okay, and then you have to use Gemini, you have to use vector AI and all those things. Good with that? Now, always industry comes with this kind of problem statements. Very vague, do not clear anything, what kind of document, how much volume, how big is the document, whether one document has 120 pages or not, whether it has table. Industry is always vague because they are users. Users are vague. You have to be technical. Okay, so now we translate that into a component diagram. Okay, if you guys are making career in software industry, search for C4 architecture. Take that now. So C4 is like how we actually do a component architecture, the class level architecture, all those things are in a sequence. So we actually give them up this kind of diagram. So how Agentic AI system is designed. Here is a user interface, communication with conversation handler. Okay, look at board. And then you have agentic workflow. The main is orchestration agent. He is the principal of the knowledge. Then you have query rewrite. Query rewrite, what exactly user is talking about. If user is asking some option, I never remember that I talked to a chatbot in proper English. I always give weird words to chatbot. Any chatbot, you ask a weird question. Never ask where, when, how, and I want this. Nothing, just keywords, right? We do that. That's a very common way of talking to a chatbot. So I need to rewrite that query for my LLM. Right? What is the intention of that user? That is query rewriting. Then query intelligence, like how do I find the context for that query? Then you have RAG agent, actually search for vector database. And you have validation agent, whether whatever is received is whether accurate according to the user context or not. Getting the point? And then of course you have prompt store and governance frameworks and all those things. This is basically a communication pattern. You have a conversation history. This is what? This is a slide which I explained, agentic memory. With me? Yeah. So agentic memory resides here. There are a number of products which will be used here, like Redis. And then we have a document capturing mechanism. Remember I told you 98%, within that the 98% fail because of data. So data actually comes from that portion of it. So basically the pre-processing or data loading. The customer is saying 20,000 documents. So we need to have a CDC, change of the capture, get that document and then convert into vector database and make it available for AI to search. So all that extraction, vectorization, chunking mechanism gonna happen there. Correct? If I give this diagram to user without a technology, user will understand this. But an architect, then he will fire me. I need to convert that into some technological words, yes or no? Because this is something which is at very high level, okay, helicopter view. Then I will convert that into, and don't get surprised, this diagram. That happens, right? Okay, so now what's happening with the web UI, Fast API, Python, is the conversational handler, you have different agentic system in Google ADK, you have prompt store coming in, okay? Then you have memory management by Google Firestore. Okay, this is all Google. If you convert that into AWS, all those things will change into AWS stuff, like Bedrock. Yes? If it is Azure, then Azure, AI services, AI agents. Got it? So all those things are listed around in Google. Then you have Vertex AI matching or Gemini model creating stuff for you. Got it? And then you have embeddings there, you have store there, you have CDC, change data capture, you have also all those things are converted into a technical term and then delivered. But does that give you an idea of how agent will work? This is an architecture diagram. So agent, you have to create a diagram like this. This is my orchestration agent, this is index identifier agent, memory manager agent, RAG agent, validator They're going to work together and do the task for me. Correct? And now I will convert and create actual agents and do and perform some duties. With me up to this point?
Yes.
All good? So this is the layer you have to think always, like understand the problem, translate that into an initial diagram of understanding and give it to your supervisor or project leader. If that is approved, then convert into technology. If that is approved, then get one step lesser, one step better. Double click on it and see where exactly classes and agents can be created. And then you create the agent. Otherwise, directly on the board, bound to failure, 98%. Got it? Okay, so I'll stop here and Q&A. Any questions? Your question is harmful, yes.
The world is moving towards zero trust for humans, and as the agentic AI is all autonomous, isn't there shouldn't be a framework for zero trust on AI as well?
We are zero trust on AI.
So can we trust agents?
No, never. I mean, see, there is always a layer of autonomicity. That's what I explained. You have to choose. The architect has to choose how much autonomous an agent should be and can be. We should not trust agent, not trust human, not trust processes.
So
Okay?
that means
Yeah.
human is the loop. Should
Yes.
we go on human on the loop?
Human on the loop for design, human in the loop for process. You are right, but the scenario is different. So for designing this, human is on the loop, obviously, but in the loop is a part of the process. Getting my point? So the final approval is always human. If that is all the industry which actually deals with the data, financial data and healthcare data, you will never have 100% autonomicity of an agent. It's not possible. The industry which is relying 100% on agent are media, blog posts. Recently you have that news clipped, right, where I can have more details. ChatGPT prompt also got printed in the newspaper. You publish that? 100% autonomicity का issue है यार वो. डाल दिया एजेंट, लिख दिया, खत्म कर दिया, अरे क्या प्रिंट हो रहा है भाई? That is bad human in loop usage. Got that? So yes, human on the loop on the architecture, human in the loop as a part of process. Okay? Good question. Very deep thought. More?
So my question is, so if we are thinking about the cross domains, so how the rack system will be like connecting with all the agents there, so that you talk about the automation agent, right? You will connect with all the agents, so that if you are thinking that if we are talking about the cross domains,
Cross domain.
yeah, different kind of domains are there, right? So how the rack system will be working on it by that it will be not getting biased towards one domain here.
It should not. You should do this, no? You should do E2A protocol. You create different flows altogether and then have those agents talking to each other. Why you are creating a single agentic system having different domain? That is an anti-pattern, isn't it? So this one is basically a right pattern for you. You create a complete agentic system for one rack, which is actually taking, let's say this is taking care of the things, and this is taking care of your financial things. And then finally come up with an output, no, you don't have money for booking. Getting my point, right? So you have a completely different system altogether. Have a API protocol is different to communicate. But having a single agentic system connecting with two different domain knowledge, anti-pattern, that's not good. Okay. Yes, last question. Yes.
I have actually two questions. First one is the difference between deep agents and agentic AI system. And second part is that when we add a MCP layer to our chatbot or something, does it convert into agentic AI?
MCP layer has nothing to do with agentic AI, it has to do with
Because it gives access to multi. Because, for example, I connect my Anthropic chatbot to a MCP, and that MCP is connected to my Twitter or Slack, GitHub, or Facebook account. So, does this system could be called as an agentic AI system? Because my Anthropic chatbot creates a plan and it assigns the different MCP servers individual tasks. So each individual part is an agent, and whole entire process is my agentic AI system. Could it be referred?
You're right. That's a very good question. Anthropic chatbot, ChatGPT chatbot, all of these chatbots are basically agentic behind the scene. You cannot perform any task without agents assigning to a different modules and actually performing and collecting knowledge for it. As a matter of fact, if you throw multiple queries at ChatGPT or even Claude, you will see sometimes two different outputs, and it actually give you like choose between these two.
because two different agentic systems actually generated those output and gave it to you. So behind the scenes are all agents. They are not pure chatbots that on directly eating the foundational model. That's not true. And including MCP doesn't make any system agentic. Agent can include MCP. MCP is independent of any system. As a matter of fact, MCP is independent of GenAI, anything. MCP is a tool and it's a it's a tool calling context protocol. That's it. How do you call the tools? Only thing. And second question is about deep agents and actually agentic AI. So deep agents are nothing but the agents which are very niche to a particular domain. Okay, so if I have a very particular agent which will always give a JSON output in 5 fields, this is a deep agent, and I can utilize that in my flow. So of course, that is part of agentic AI. Only thing is we sub-branched it into something new. Okay. Awesome. So we'll stop here. I think I am not going. Yes, please, sir.
Software development and
Software re-engineering, very modernization. So, I mean, it's not direct, but all these new copilot and how software like cursor are behind the same agent. What they do is they
and quantum optics, a central figure in India's national quantum mission. So was instrumental in establishing the nation's first quantum technologies hub, bridging the gap between fundamental science and industrial application. His current technical focus includes the construction of ion-trap quantum computers and high-precision quantum sensors. Beyond the lab, he has cultivated a robust quantum ecosystem, graduating 9 PhD students and mentoring the launch of 2 successful quantum startups. SIR continues to drive the commercialization of quantum 2.0 technologies, translating complex subatomic control into scalable and real-world solutions. We are honored to have you, sir. So may I now request you to address the gathering. Please welcome him with a huge round of applause.
Good evening. Thank you very much, and my pleasure to be here, and thanks to the organizers for inviting me for giving a talk. After listening to the first talk, it's going to be a big challenge for me to convey the ideas about what I'm going to talk about to the audience now, because I think most of you are from computer science background, right? Most of you are not. I don't know when you did your physics courses last, but maybe 12th standard. How many of you did physics? All right. How many of you heard the word quantum mechanics? Most of you, right? Yeah, okay. So I think then I'll start from very basics in this, and then try to touch upon what quantum computers are and what they are going to do. Okay. So okay. There is a lot of buzz going around, right, about quantum computing, especially about quantum computing, and there are many other things in quantum technologies other than quantum computing. So, but most of the eyes are on quantum computers, and everybody reads about quantum computers. And there are some companies which have created a lot of buzz around quantum computing, and also the training around it, and many aspects, right? Before I get into this, what quantum computers are, I'll just give you a basic initial ideas about what are those things about, what is it that is quantum in everything that people are talking about, especially when you hear about future computers are going to be, they're not going to replace classical computers, but they're going to add as additional accelerating hardware for existing computers so that one can solve very difficult problems. And when we say difficult problems, I will come to that, what difficulty means in solving a particular problem. Now, there are four things that are very counterintuitive when you talk about quantum mechanics. Four physical aspects about quantum mechanics, or things that happen at a very at a scale, at physical size scales which are at the atomic level. Okay. Now, things like, for example, when you in classical world, in our day-to-day world, when I bounce the ball, when I throw the ball on the wall, it's going to bounce back. But something different happens in a quantum world. When an electron tries to cross a barrier, it's not going to completely reflect back. There is a probability. Hear this word carefully, probability. Okay, quantum mechanics is all probabilistic. When the electron bounces or goes and hits the wall 1,000 times, not 1,000 times it is going to reflect back. It's going to go through the wall for some number of times. Now, this number of times it goes through is what is decided by quantum mechanical probability. Okay. Now, this is like saying that when you can look at a scenario where you see, say, a sodium lamp in the street, the orange lights. The light is because of a particular specific color, because the electron is jumping from some higher energy level to a lower energy level, and the electrons are taken to the higher energy level by some electrical power that you feed into the bulb. Okay, by some collisions with other atoms, you excite these, and then the electrons are going to decay, and it emits orange light, which is at certain specific wavelength. Even this specific wavelength, existence of specific wavelengths for sodium, or if you take a mercury lamp, it has specific set of wavelengths of light that it emits, and all combined together it looks like a white light because it has a composition of many different wavelengths. Now you take hydrogen atom, it has certain specific things. Now why all this happens is because of certain very fundamental principles of quantum mechanics. And one of the things is basically at a quantum level, particles don't remain as particles. They behave like waves. They behave interchangeably as particles and waves. Okay. This is very counterintuitive. I mean, everything that we see in our day-to-day life is some physical object with some specific shape and size. And if a ball is moving, if it's a cricket ball, it's moving at certain velocity. And at each point, you can find out what its trajectory is going to be by simply writing down Newton's laws of equations, and then you can calculate the trajectory of this part of the ball in the space. Of course, if there is an unexpected wind, it becomes difficult, but assuming that there are no turbulence, there is no wind or turbulence, it's easy to calculate. Now, at quantum level, it becomes very difficult, very fuzzy. Particles are not particles anymore, they behave like waves. And once this wave nature enters into the description of these systems at those microscopic scales, what happens is you talk about things like this superpositions, which is written. It's like this, in a water pond, you drop a stone, you get waves. You drop two stones, each one will have its own set of waves, but then when they come together, they are going to interfere with each other. And then there is going to be, both of them are going to add at some point. So that is this superposition. And other thing, which essentially means that any quantum mechanical system like that electron which was in the ground or the excited state, it will not, it need not remain in completely ground or excited state. It can remain in a superposition of these two states. I will come to that in a moment. And then there is something very important resource that exists from quantum mechanics which you use to overcome the limitations of classical computers, which is called as an entanglement. If you had a single electron in an atom, it could be in the ground or the excited state. But if you had two different atoms, in these two different atoms there are two electrons belonging to this atom and this atom, they can be both either in the ground or excited or vice versa, and there is no correlation between which electron, if one electron is in the excited, the other one has no relationship with that. It can be anywhere. But in quantum mechanics, it is possible to create such a scenario where this electron, the state of this electron in these two of them can be correlated. And that is called as an entanglement. Entanglement is a very complicated, complex subject, but I'll spend another minute in explaining entanglement with some other example, which may not be 100% perfect because there are a lot of mathematical nuances in that, but I'll try to give you a small picture about, intuitively you can try to understand. Now if I take one ball which is half white and half painted, half white and half black, I scramble this ball, meaning I rotate it in random direction, it's spinning in random direction and I throw at it. You catch the ball, you see either, say you have only possibility of seeing white or black. You see either white or black. Now I take two balls, I do the same thing and throw at two different people. Both of them will see either black or white, completely random connection between the two. If the other guy sees white, there is no, you cannot predict what this other person is going to see. But there is something that can be done, or that happens in quantum mechanics, is that when I throw this ball, I do some magic in my hands, and I throw it at each of you. Individually, if you look at the ball, 1,000 times I do this experiment, every time you see it either can be black or white, with maybe equal probability. Other person also can see either black or white with equal probability. But something else that happens is that one person can predict what the other person is going to see by just looking at what he sees. If I see white, I can create that entanglement in such a manner that when I see white, most of the times the other person is going to see white only. You can also make that magic, the entangling operation, in such a manner that if I see white, I can predict that the other person is going to see black. So this or black. So this kind of strong and strange correlations that exist in quantum mechanical systems is called entanglement, and it's a big resource in quantum computing. Wave particle duality I told you, tunneling I told you already. Now, the difference between your classical computers and quantum computers. At the very heart of it, at the base, inside your processor, the way computations happen is that you have some, your information is stored in terms of zeros and ones with some number. These numbers are stored in some registers. These numbers are temporarily stored in some registers, or for a longer time stored in flip-flops and all that, basically flip-flops, which are your memory devices, or you have a combinatorial logic which you apply. So two types of logic, combinatorial and sequential logic, which you apply on your bits to do all your computations. But at the end, inside there is some transistor which is basically either switching on or off to define that bit, or the logical, the voltage levels, where you define that above this voltage level it's logical 1 state or logical 0 state. Okay, so that's what it is. And then you build your gates with these transistors, and then from that bottom up you build all your complex processors and whatnot you want. In that case, the universal gate that you should be able to build is the NAND gate. Once you build a NAND gate, then you can build all types of gates. Now, in a quantum mechanical system, I have given two examples. One is that electron in an atom. This is an example of one particular ion which we use, but forget about everything. There are two levels in which the electron can basically say the ground, low energy level, and some excited state where you excite the electron. Now these two are your logical 0 and 1. Okay? But hold on, it's not just that 0 and 1, I'll come back. Then you have photons, light. Light can have two states of polarization, basic states of polarization. That is linearly polarized. You can also have circularly polarized light. But let's consider linearly polarized light. It could be horizontal or vertically polarized light. These are the two states of the photon. And if this photon polarization is in some other state, whenever you do some measurement of the state of the polarization, it's going to give you an answer of the photon being either in horizontal polarization state or the vertically polarization state. Now, in classical computers, you have only these two states, I told you already. But in a quantum computer, when you use these quantum mechanical systems, the electron can be either in the 0 or 1 state, which is your on or off state comparing it to the classical state computers. But it can also exist the state of that qubit or the bit, which is called as a qubit when it's a quantum bit. It also exists in some fraction of this 1 and 0. Now this A and B, A times 1 plus B times 0 is the complete state of that quantum mechanical system, which is the qubit. Now this A and B are complex numbers. They are not simple numbers as the real numbers. They are complex numbers, which also come with phase and all that. However, the square of A square plus B square will remain 1 because of certain reason, but nevertheless, you can basically have a quantum mechanical system. That electron, which I said can be in the ground or excited state, can also be 50% of the times in the ground state, 50% of the times in the excited state. So that's the superposition. I told you quantum mechanics is probabilistic. When I excite that atom in the excited state or the ground state, I cannot definitively say whether that electron is in the ground or excited state unless I do a measurement. And when I do a measurement, if I create, say, a system with completely in the excited state, 1000 times I do the measurement, almost 99% of the times I will get the answer that the electron was in the excited state. Rest, it will be in the ground state. But if I created a superposition of 50% and 50%, I do 1000 measurements, 1000 times I look for where the electron was, I will get an answer that, okay, 50% of the times, 500 times randomly of course, I will see that the electron is in the ground state. 500 times I see that the electron is in the excited state. That's if I had one quantum system, like one electron or one atom. But if I had a million atoms, when I create a superposition of all these million atoms, every time I look at the system, 50% of the particles or the atoms I'll see them in the ground state, 50% of them in the excited state. So this is the probabilistic nature of quantum mechanics. Now, in general, to understand the qubit state, which is where all the physics of the gates of the quantum gates that comes in when you try to see this IBM's Qiskit programming and all that, most of the times you will encounter these gates, different types of gates. And I'll explain, there are two types of gates that you need for a quantum computer. You cannot, like in a classical computer, you just need a NAND gate. In case of quantum computers, you need two types of gates. That one of them is called a single qubit rotation gate. And I told you in the previous slide the superposition, right? And A and B are complex numbers. Now, the state of that qubit or that electron can be represented on a sphere of unit radius, of radius 1. The poles of this sphere will be your 0 and 1. And if your quantum state was in either 0 or 1, you can represent it as a vector from the 0, from the origin to the pole. So say north pole, then it will be in 0. Now if it were in a superposition 50-50%, then that point is represented on the equator. But where on the equator depends on the relative phases of those A and B that I had in the previous one. And I can also flip the vector completely to the south pole. So this is like rotating the state of the two-level state of that qubit on this sphere. Okay, so this is called as a single qubit gate. And along which axis you rotate, or by how much you rotate, completely by 90 degrees or 180 degrees, all these correspond to, I don't know how many of you have seen this Qiskit programming for quantum computing, but whenever you come across that, you will see these X, Y, Z gates, and all those basically essentially mean that how you are playing with the superposition of the ground and of the 0 and 1 of that qubit. And basically on this sphere, where are you rotating that vector from which point to which point? So this is a single qubit gate. But just to give you another example of the power of where the power of computing comes from. If I had a single qubit, I am representing that state on that sphere, north pole or south pole by these arrows. So single qubit can be either up or down, but also a superposition of 0 and 1. If I had two qubits, then there are four possibilities. Both can be up, both can be down, or one of them can be up and down, and vice versa. So you have four possibilities. Now for two qubits, you can create a superposition of these four possibilities because of this entanglement operation, even though they are independent. And if I take three of them, I can create 8 possible states. All up, all down, one of them up, or two of them up, and then the other combinations. Now imagine if you had 300 qubits, you have possibility of so many states. This number of possibilities is so large that it's just even larger than all the atoms that exist in this universe. Where it's like 10 to the power 90 times. So if you have X number of qubits, the amount of possibilities that you have, that you get in terms of storage of information is just unimaginable if you compare it with the number of classical bits that you have access to in your classical computers. Okay, so that is the power. Now, the question is, okay, so what? I mean, where are we going to use this computer, quantum computers, right? I remember I said initially, these quantum computers are going to allow us to speed up computing. Now, when you say speed up, it's a very tricky question. If I have certain problem, I'll say that, okay, I'm running it on my laptop, it's taking 5 minutes. I'm running it on my mobile phone, maybe it takes, I don't know, 10-15 minutes. Or if I run it on a cluster in my office, it may take 1 minute, and somebody says, no, put it on a high performance computer, a big supercomputer or something, it will run in 1 second. Now, this is not speed up, okay? This is not like you put all the horses to work and you make it run faster. That's not the point. Point is simple. You take any problem will take certain amount of time to solve it, depending upon the size of the problem. Okay? And you look at how the time scales with the size of the problem. I think these are classic computer science problems, right? Okay. So, for example, there are class of problems where the time taken goes as a polynomial function of the size of the input, means size of the problem. Okay. But there are certain problems where the time that it takes to solve them increases exponentially longer with the size of the problem. So these are slow problems, these are fast problems to solve. Now that's where you compare whether your processor is going to bring down that, speed up the problem by making a exponential problem into a polynomial time problem. Okay, that's what is speed up. This is where. So some examples are, for example, if you look at the problems which take whose time goes as a polynomial in the size of the problem, are problems like this matrix diagonalization or searching through some databases which goes as the time goes as the order of n. Now this problem, the slow problems, are problems like this maze problems. If you had a small maze, it's easy. You can find out where you know the start point, end point, and you can trace the path which is the shortest path. Now, if you increase the size of the maze, it becomes very big. It becomes unimaginable. This is still, this can still be solved. But if it's a much larger maze, these are slow problems. Now, they will be slow on any computer, of course. If you put it on the world's most powerful computer, it will be fast, but it's not. That's not the point I'm trying to make. Now, remember the superpositions I told you. Superpositions and entanglement. Okay. Probably. So it's like this is a wrong example, but I'll still start by giving that example. In a laptop or in a desktop, you have a single processor. Okay, maybe there could be many cores in that. That's a different thing. But there are certain problems where you can actually break down your problem into many units, which need not be solved sequentially. So you can break down your solution to the problem into different parts and give each of these parts to a different processor. So this is parallelizing your problem. So what you do is that instead of one processor, you use a cluster of processors, tie everything together, maybe thousands of them, or even, I don't know, tens of thousands of these processors you put together and break your problem into so many, whatever number of units you can break it into. It depends on it becomes very problem specific. Then you run parallelly on these processors and you execute the problem. Now, in a quantum computer, something like that is happening, but there is a very subtle difference. It kind of, because these the quantum mechanical bits, the qubits, they can exist in superpositions, they can be entangled together. When I create a state, or when I imprint the problem onto the set of qubits, I am actually imprinting that problem into this set of superpositions and entangled states, which allow me to solve this maze problem, not like this, but like this. Essentially what you are doing is that you have a single processor which can work in such a manner that it is going to explore all the possible paths simultaneously with a single processor. It's not like multiple processors are exploring or solving the different parts of the problem independently. It's like all the processors, a single processor is actually exploring doing the job of many processors at the same time with a single processor. Something like that. I mean, crudely you can imagine that, just for your understanding purposes. Now, why this quantum computing business, this entire field started getting a huge push in the recent times? Of course, this started almost 30 years ago. And I have been in this for 25 years. I mean, we have been working on quantum technology. But only in the recent times there has been a lot of buzz that has been created. I'll come to that why the buzz has been created. Now, one of the classes of problems where they are considered as difficult problems to solve is this prime factors, factorization into prime numbers of a big number. Now you take a small number like 15, you can just do it in a short mentally that there can be these two prime factors of that number. If you take a large number, okay, it will take some effort. Now if that number is very large, like I don't know, 1000 bits number, it becomes completely impossible to solve that into two prime factors using any computing power that you have on the earth in some reasonable time. You may have to wait for, I don't know, months or years. There are numbers of that. People have estimated that it is impossible to get prime factors. Now, why is it important? It's some pure crazy mathematics problem, right? That is important because all our information exchange, all critical information exchange, relies upon that particular fact that you cannot factorize large numbers for encrypting your information. And that's based upon this so-called RSA crypto system. This works on the principle that you cannot factorize very large numbers into prime factors using any computing power on the world. So that is one very important aspect where quantum computers will play a big role. And that was the fear because of which quantum computing took a lot of attention from all the big countries and across the globe. Because Peter Shor developed an algorithm in 95 or something, I forget the year, where he came up with an algorithm using quantum mechanical systems, qubits, and using the principles of this entanglement and superpositions, and showed that you can actually factorize very large numbers in polynomial time as opposed to exponential time because of these delicate quantum mechanical features of superposition and entanglement. So that's why quantum computers have got a lot of attention. But then, other than that, that was the initial problem, but there were other problems which have been shown that on quantum computers you can actually speed them up like anything. For example, if you look at this maze problem in practical applications, if you are looking at a very big logistics chain company, okay, if you had, I don't know, 1,000 destinations, 1,000 places where you pick up your material that needs to be delivered and you have very few resources. If you had only say 10 trucks and you have 1,000 destinations and you have, I don't know, 1,000 more places to pick up your material from. If you want to optimize your entire route of picking up and delivering, that problem is also an exponentially those problems also take exponentially longer time. Those kind of problems also can be solved on quantum computers. So in fact, these days, whatever small computers that exist now, people are actually using them to develop algorithms for these kind of things. Okay, I'll skip this wave particle to that. So other things where you can use this, it's not only for quantum computing, okay? When you talk about quantum computing, one of the things that is, one application that is very important and gaining traction these days is doing chemistry, which is relevant for, say, designing new molecules for fighting diseases. Typically, if you go by the traditional route, if you take classical computers and you want to design an interaction between one molecule with the other, typically it's like in pharmaceutical or medical science, the drugs, the medicines that you take, they are most of the time designed in such a way that they target specific molecules in your body, either to inhibit certain physiological reactions or whatever, or to enhance certain things. Now all this depends upon how a molecule A fights with a molecule B, and this could be anything. Now just to look at this dynamics of how this happens, people do things like the screening of drugs. So you have a molecule of your body and then you want to know which particular one binds to this in a specific manner. So you try with many molecules and it's a very time consuming process. Now if you want to do it on a computer, you have to simulate the structure of these molecules from first principles of quantum mechanics, starting from atoms, how they build into that particular molecule, and then you look at all this. And when you do this on a classical computer, since you are starting from first principles of quantum mechanics and write all the equations of motion, Schrodinger equations and whatnot for all these atoms, the problem becomes so big. As soon as you go beyond like 10 or 15, 10 atoms or so, 10, 15 atoms, you will start feeling the need of using supercomputers. And it takes a long time. Now, so those problems, as I said, if you use these quantum bits or quantum mechanical systems, you don't have to know the quantum mechanics and you don't have to put the equations. The nature takes care of itself. You put two molecules kind of a system that you design physically, a real system, and then you bring them together, you know what is happening with them. And that's like an instant solution to the problem. So that is one way of solving this problem. Of course, there are other areas like for designing new materials, in healthcare, for civil engineering and for building better and better atomic clocks. Why I am giving these other examples is that this is not quantum computing, but these are applications where you use those principles of superposition and entanglement to make sensors, say for example, which can detect underground tunnels, or maybe there could be a sinkhole. Like for example, you see some pictures on the internet, sometimes there's suddenly one road has just sunk inside, right? Because of the there is no way to survey the land to see that there is suddenly there is just this quicksand kind of land underneath. If you do this sensing with quantum sensors, you can know suddenly there is a very lack of earth density somewhere, so that you don't build roads there, which will just sink after a few months or years, right? So those are some applications. Other applications are which will allow you to do GPS navigation with a millimeter accuracy. Right now it's a meter kind of an accuracy, but when you are talking about using these things for defense applications, for navigation, you need much more accuracy. Or for example, you want to do navigation where there is no GPS, for example, either in deep space or when you are going on a war, and then all the GPS systems are shut down by the countries that operate that, your sun. So you need autonomous navigation systems for which these are used. Anyway, I will come to this. Don't forget about all this. This is a one slide big poster which was created by somebody, which basically gives you a complete landscape of all this quantum computing. It starts with what are qubits to what are the different physical platforms that people are building, and then they also talk about different algorithms which are being worked upon to overcome this problem for the hard, to solve these hard problems. Now, I will talk only about the few computing hardware. How much time do I have? Okay. So right now, when you look at what are the things available computing wise, quantum computer, real quantum computers, they are based on different platforms. So for example, on top here, these are the three platforms by these companies called IonQ, Honeywell. Okay, it's a continuum. And then there is a company in Innsbruck where I work, not work, at the university where I work. And then the superconducting qubits, which is made very popular by IBM. And then there are a couple of companies which have demonstrated quantum computers with neutral atoms. All these dots that you see here, they are basically individual atoms which are used as qubits. Like for example, same here, each of this is light from a single atom. Now superconducting, so I'll just go quickly over this different platforms what they are. Superconducting qubits, neutral atoms and trapped ions. In superconducting qubits is basically a pendulum, electrical oscillator, like an LC circuit, which is formed by, instead of that inductor, you replace it with a Josephson junction. So this is a Josephson junction, it is basically a loop of superconductor with some small break in between. So once you pass current through it, the current inside this oscillates back and forth, and you can create an oscillator with an equivalent circuit like this with a non-linear inductor. I hope you understand LC circuits, right? In LC circuit, when you put current through it, it will start oscillating if you overcome the damping. Now in this case, instead of the inductor, it's a non-linear inductor with this Josephson junction, and it creates this different energy levels which have a definite spacing, because it's a quantum mechanical oscillator, not a classical oscillator. Now some of these energy levels separation is such that unless you take the superconducting qubits down to a few tens of microkelvin, millikelvin, you cannot resolve those, and those you use as the quantum mechanical energy level diagram. And they are like, you put them in some kind of a cavity and excite them. And then you have electronic spin qubits. So what you do is that it's like these semiconductor devices. You create a two-dimensional gas of electrons, which is basically, it's just 2D. In the third dimension, it's just one electron kind of level. You put electrodes and then you confine single electrons by putting these electrodes, and then these electrons will act as qubits. Now I will quickly focus on these two platforms which we are working on in IISER Pune. One is the ion trap quantum computer and the other one is neutral atom. So in both cases what you are doing is you are arranging atoms in a very specific manner, like a register, and you compute with them. Since I have little time, So I'll briefly tell you about how these ions can be used for computing. So this is an image, from a camera taken of light emitted from 3 of those qubits. Each of these qubits, they are separated by about 5 micrometers from each other, and 3 of them form a quantum resistor. They are like, you can imagine them as masses suspended by springs here. And then you can individually excite these ions, and then you can also shake all of them together, which is essential for entangling the qubits. Now these ions are trapped in some electrode structures like that, like these 4 rods, and they can be of different configuration, but we use something like this configuration, where you basically apply radio frequency across the opposite electrodes to stabilize the charge in free space. Now, why ion traps? Ion traps because these qubits are the purest qubits. So whenever you talk about these quantum mechanical systems, they are prone to errors. There are they interact with the environment. Their state can flip randomly. Now that leads to what are called as error rates in quantum computing. So they are working on a lot of these error reduction techniques, error correction techniques in quantum computing. And in case of these ions, in ion traps, the error rates are very low. So you need very less qubits. You can work with lesser number of qubits than having larger number of qubits, which are used for these error correcting codes. Now, one configuration where you can think of is something like this, like a racetrack, where you have ions which are stored in certain zones, and then you move them around, make them interact, apply a 2-qubit gate, move them away and things like that. So you get complete connectivity. You can imagine these qubits as every qubit connected to each other qubit. Now this is a picture of different number of qubits in our trap. This is a single ion, it's a single atom, and there are 25 of them. So by focusing light on each of these qubits, you can change the state of that qubit from 0 to 1. And the way it looks like when you change the state of the qubits is like this here. You see them blinking. So whenever it's dark, it means your qubit state has changed from 0 to 1. And whenever it's bright, the qubit state is in the ground state. So whenever you do quantum operations on this, the quantum gates, your qubit states are changed in this fashion. This is for some particular case scenario. And then you read out the state of the output of your computing operation. Now, our trap is something which looks like this, which is inside an ultra-high vacuum chamber, and inside these electrodes you trap these ions. And within the ion, forget about all this, there are 2 levels of the electron. This is the 0 level and this is 1, which we call logical 1. On this we excite with a light to change the state of the qubit, to rotate the vector or to rotate the state of that qubit. And there are a lot of complex things around it. The entire room is filled with a lot of electronics and vacuum chambers and lasers. Now, okay, if you look at this diagram here, this is actually when we are rotating the qubit on that block sphere from 1 to 0 and so on. So each of these oscillations, it's a population of the ion, the electron state, whether it's in the ground or the excited state. And when you apply gates, you essentially turn on some laser for only say this much time, you can completely flip the state of the qubit. Or if you apply for this much time, you flip it, take it up and bring it down, and so on. So those are the quantum gates that you apply on this qubit. Now our roadmap is basically to go from, by this year end we will have a quantum computer, we should have a quantum computer of about 1,000 qubits, and if you look at the state of the art, and this machine costs about $200 million, they are at about 98 qubits now. We are planning to go into that, and this actually they are working on many problems, like they have a investor from a big pharma company and other companies, and they are working on developing these algorithms for drug discovery and many other things that they are already doing. This is another example. This is a spin-off from a university in Austria where I had worked. They have some 20 plus students. Yeah. So I will stop here because I don't have time. I wanted to talk about the other platform, but I will stop. What should students do to pursue career in quantum? Okay, so I mean there are many aspects in quantum computing. Of course, the hardware aspect is one, and then there are the software aspect. Like when the first processors were built in the classical computers. Earlier people used to do with assembly language, and then slowly it progressed to languages where humans can actually intuitively program things and which can be compiled into languages where it would work at a machine level. Now this is the same era that we are in with quantum computers. There is a lot of demand and work going on developing algorithms for real life problems for quantum processors. Okay, because it's a different ballgame altogether. It is not just simple Boolean algebra that one has to do. It has to be, it is much more beyond just Boolean algebra, right? Because of the superpositions and entanglement. So that is one area where there is a lot of demand now on developing quantum algorithms, which is all software. It then doesn't matter which particular hardware, which particular platform you are going to use as a quantum computer, but at the top level, the algorithm is going to be the same. Then second is converting those algorithms into quantum circuits. Meaning, when I said you apply single qubit rotation gate, you apply 2 qubit gate, these are at the level of the quantum processor. Now, how do you convert your algorithm into a sequence of these gates? So that is another area. Then there is, as I said, these quantum mechanical bits are very fragile. There will be a lot of error rates depending upon whether how the system is interacting with the environment or which platform it is. Some have large error rates, some have less error rates. So there is a big area where people are working on error correcting codes. So if you want a proper logical qubit, single logical qubit, sometimes depending upon the system, you need 3 qubits, additional 3 qubits or additional 5 qubits. So these are additional resources. So if I want to make a 100 qubit, 100 logical qubit processor, then I might need 500 physical qubits. How to optimize that? That is one area. So these are in the purely software side of things. On the hardware side, of course, there are so many things because 5% of the entire quantum computer is the physics part of it, physics engine. But of course, that's 90% difficult problem also. But the rest of the 95% is all classical electronics and computers and control systems and everything which go into building that. So one has to see which area one needs to get in.
And sir, my one question that to do research in quantum computing on sir degree, or if we can do that by our own knowledge and our experience.
Yeah.
Yes.
So quantum computing, as I said, when people do research or PhDs in quantum computing, as I said, these algorithms areas, error correction, using different platforms, how to use different platforms, there are many such things. So you have to figure out where you want to go, and then there are different research groups who are working on those within India and abroad?
Sir, I want to take in my part for 2 years. I studied content development and then do a lot of research on some algorithm, general equation, and just binary, just double slit experiments, photons, and a lot of I wrote my thesis elsewhere, and I want to do more advanced research, and I want to study more in detail. What should I do for it?
He is pursuing computer degree, so his question is that whether he has to go for additional certification or some diploma, what he needs to study, because he is interested in pursue career in quantum.
So I think you should first look at doing some post-graduation degree in quantum computing related subjects. But since you are probably a BTech student, you can also get into PhD programs, but you need some physics knowledge also.
Yes, sir. I study physics a lot, and I study by my own. So is degree is necessary or just an optional, or I can do by my own?
No, I think you should do some formal training. Yeah, PG or even.
And also Bitcoin blockchain.
I have a graph picture of where we are, but not in this. Let me see if it's online.
Speaker.